What happens to our best mathematical tools when the variables stop behaving like numbers and start acting like matrices? In classical computing, Talagrand's inequalities are the gold standard for understanding how local changes affect a global system, but applying them to quantum mechanics has been notoriously difficult due to non-commutative algebra. This paper establishes a new framework to bridge that gap. Let's start with the core problem. In the classical world, we know that the global fluctuation of a function, or its variance, is strictly controlled by its local influences. However, when we move to the quantum Boolean cube, the order of multiplication matters, effectively breaking the standard tools we use to measure these relationships. The researchers set out to fix this by finding a dimension-free inequality that works even in this complex environment. To solve this, the authors moved away from traditional combinatorial counting and adopted a heat semigroup approach. This essentially models noise diffusing through the system to smooth out the mathematical functions. They introduced a specific alpha interpolated gradient, which creates a clever bridge between local variance and instantaneous change, allowing them to handle the non-commutative nature of the quantum variables. This approach yields the first rigorous quantum Talagrand inequality. The researchers prove that the total variance is bounded by the gradient's norm, typically achieving a significant logarithmic improvement in precision. Crucially, they extended this theory to cover high-order influences, meaning they can now analyze the structural trade-offs for entire groups of qubits at once, rather than just isolated particles. The impact of this work goes beyond pure theory. It provides a concrete toolkit for analyzing how sensitive quantum algorithms are to noise. The findings are robust, featuring explicit constants rather than vague estimates, and they successfully recover known classical inequalities as special cases, verifying that this new quantum framework is consistent with established history. By solving the non-commutative puzzle, this paper successfully translates powerful Boolean analysis tools into the quantum domain. For more details on this theoretical framework, I encourage you to visit emergentmind.com to explore the full findings.